We've seen how to use the divergence test, the p-series test, and I alluded at the last video at the end of it that the integral test is kind of a bit. Now, it's something that you can use when, you know, the divergence test really doesn't probably give you anything, or the p-series test almost doesn't really give you much. There's a lot of heavy lifting that you got to do here, but it can kind of give you a useful result. So in this video, we're going to talk about the integral test. So we're just going to go ahead and start with the theorem here. Okay, so this is straight off the text here. We have the integral test. So let's suppose I have some infinite series, okay? Say a sum starting from n equals 1 to infinity, okay? I don't have to start at 1, but possibly at 1, okay? I have a series with some positive terms, an. So that means all these ans, okay? An is positive for each n, okay? Now, let's say that I can choose a function f. There is a function f and a positive integer capital N for which the following are satisfied. F is a continuous function. It is also a decreasing function. And if I evaluate f at any integer n for any n after this big N, that's a weird statement. I basically get the sequence back. So basically, that function is the continuous version of the sequence. Okay. Then here's our result here. Here's our big result. Both the sum and the corresponding integral from capital N to infinity both converge or they both diverge. So the integral test has a few things. Okay, first, you need a series with positive terms. That's very important for this theorem, okay? You need a series with positive terms. Now, after you have determined you have a series of positive terms, you have to make sure you can choose a function f that is continuous, decreasing, and you can actually map it to the sequence, such that we can extend this to the real numbers. Then, when you take the integral, both of those converge or diverge. Now, there's a few technicalities here that we would be careful with, okay? But the biggest thing here is to check that this holds. This is important. You have to make sure that you have a decreasing function. You can do this with either inequalities, that's the, shall I say, the pro way, or the way you usually do it in Foundations of Analysis or Real Analysis 1, or use the first derivative test. Okay? And we'll see some examples of that. Okay, so for the integral test, you need to make sure you have a function that is continuous and decreasing, and sort of by consequence positive, okay? Eventually decreasing, rather. And all you have to do is look to see if the integral and the sum behave the same. If the integral converges, the sum converges. If the integral diverges, the sum diverges. So let's actually go ahead and see this in action. We have a sum here from n equals 1 to infinity, n over 1 plus n squared. We want to use the integral test to see if this series converges or diverges, okay? We need to justify our answer, okay? So we're going to go ahead and set up the arguments here, okay? Now, I'm going to go ahead and kind of spoil this for us, okay? You don't have to do this at the start, but I'll go ahead and spoil it for us and say that I'll make the claim here that the sum diverges. And we're going to go ahead and prove this claim. Now, the first thing that we need to do is extend this to a continuous function. And the way we do that is we're just going to replace the n's there in our summands with x. So we're going to go ahead and let f of x equal the function x over 1 plus x squared, okay? That's all we do. We just go ahead and replace n, which is usually a discrete variable, to x, a continuous variable, okay? Now, this is certainly a continuous function, okay? If you remember from Calculus 1, okay, this is a combination of two functions that are continuous on the domain from 1 to infinity. Okay, so certainly, okay, this we don't really have to justify, but we'll just write it down. So certainly f is continuous, if I can spell. F is continuous on the interval from 1 to infinity, okay? Now remember that this interval notation, right, that just means x greater than or equal to 1, okay? So in this case here, okay, our capital N, for the moment, Our capital N is 1, okay? Now we need to show that this function is decreasing on this interval. That's the next step, okay? So now let's take the derivative. Okay, if I take the derivative of my function there, okay, we're going to go ahead and use the quotient rule from calculus, okay? So go ahead and give yourself a refresher on the quotient rule if you need to, but I've always said it the same way for a few years, and by a few years, I mean 12 years at this point, okay? Quotient rule. We have the bottom times the derivative of the top, derivative of x is just 1, minus top x times the derivative of the bottom. The derivative of 1 plus x squared, 2x, just power rule. Okay, all over the bottom squared. 1 plus x squared squared. Now, when you tidy everything up there in the numerator, okay, you will get 1 minus x squared over the square of 1 plus x squared. Okay, so we have a derivative. Now we need to check where this is negative, okay? Now, this is a fraction, okay, and notice that the denominator, okay, 1 plus x squared squared, that denominator is always greater than or equal to 0 for all x. Okay, whenever you square a number, it is always positive, okay? We need to check. So it remains to check, or rather solve, 1 minus x squared is less than 0. So we need to figure out where this function, the numerator, is less than 0. Okay? Now, how do we do this? Okay, if we remember from algebra, we can go ahead and make ourselves a little sign chart here. So let's go ahead and do that off to the side here. Let's do this in pink. So here's 0, 1, -1. Okay, and I'll remark here that I can factor the left-hand side. 1 minus x times 1 plus x is less than 0. Okay, so the way that we solve those polynomial inequalities, right, we find the zeros, so we factor it, find the zeros. The zeros are precisely at 1 and -1. Okay, so now my number line is in 3 pieces. Okay, I won't show all the details here, but if you pick a test point inside each of those regions, so a number between -1 and 1, a number bigger than 1, and a number smaller than -1, you will get the following results. From -1 to 1, okay, that function is plus there. From -1 all the way to the left, that's minus, and 1 to the right, that's minus as well. But because we're only working with positive x's in this case, okay, look back up here. Since we're only looking at this range here, I don't care about what happens when x is less than 1. So I don't care about those parts there. Instead, all I care about is here. That's the good spot. Okay? So, that function, okay, that 1 minus x squared is less than 0 when x is less than 1, okay? So this, excuse me, greater than 1. So this holds when x is greater than 1, okay? Well, what does that give us? That thing is negative. That was the derivative. So the derivative is less than 0 when x is greater than 1. So f is decreasing. Okay, f is decreasing on that interval from 1 to infinity. Okay. Now, to be kosher, I should have put like an parenthesis there at the 1, but it doesn't really matter at this point. Okay. So we have that f is decreasing. We have a continuous function. Okay, and I've mapped and I've extended it to the real numbers. So now what do we do? Take the integral. Okay. So now we're going to go ahead and look at the integral. So we're going to go ahead and integrate our function from 1 to infinity. So we have the integral from 1 to infinity of x over 1 plus x squared dx. Okay, you can go ahead and do a u substitution here, okay? Or if you've gotten used to it, you can kind of see the pattern already, okay? But we'll go ahead and do the following. I'll go ahead and write out what the u substitution is. U is equal to 1 plus x squared. And so du is 2x dx. Okay, and then doing the usual stuff here. Okay, when we change variables, okay, we'll have a 1/2 times du over u. Now our integral is going to range from, let's see, 2. Okay, let's go ahead and erase that. From 2 to infinity du. Okay, we do the usual thing for improper integrals. We pass to a limit. Okay, so this is the limit as t goes to infinity of the integral from 2 to t of 1 over 2u du. Okay, and this is straightforward. Okay, just use our little rules here. This is the limit as t approaches infinity of, we have 1/2 of log of absolute u, okay, from t to 2, okay. And now take a look at what remains, right? We have this limit here, 1/2 of log absolute t minus 1/2 of log 2. But notice that as t gets large, log of t gets large. So this entire thing gets large. So the integral is infinity. Okay, so as the integral diverges, okay, let's see if I can make a complete sentence here. So as the integral is divergent, sum is divergent by the integral test. Let's go ahead and fix that. So what do we have to do here? Let's go ahead and recap. Integral test. All right, let's go ahead and recap what we had to do here. Okay. Step 1 was to choose your function. Okay. Step 2 here is to show that it's decreasing. We can do that with inequalities or the first derivative test. Okay. And then step 3 here is to go ahead and do the improper integral. Okay. So those are your 3 steps for the integral test. Okay. You choose your function, check that it's decreasing. Okay. Take the integral, and then your conclusion follows. Let's go ahead and do this one here. This time we have, well, this one should actually start at 2, because if you notice here, log of 1 is 0, and I can't divide by 0. Okay, so this should actually start from n equals 2 to infinity, okay, for it to make sense. 1 over n times log of n squared. Okay, I'm not going to go ahead and give a claim to see if this converges or diverges. We're going to go ahead and figure it out, okay? So let's think about step 1 here, okay? Step 1, we choose our function. What's our function here? Well, just replace the n's in there with an x. So let f of x equal 1 over x times log of x squared. Now we're going to go ahead and show that this is decreasing, okay? So step 2, and I'll write it like this, okay? We show by the first derivative that f is decreasing. So we're going to prove that f is decreasing. Now, there is a way you can kind of shortcut this. Whenever you have like a reciprocal like this, where it's just like 1 over a function, if you want to show that entire function is decreasing, you can show that the denominator is increasing. But that's an exercise I can leave for y'all, okay? But we'll go ahead and just do this with the first derivative test, okay? Okay, just as an exercise, okay? So we'll go ahead and take the derivative. So f prime of x. Okay, we're going to go ahead and have to use some trickery here. In fact, I think we'll go ahead and just use the quotient rule. You could use the power rule if you wanted to, or the product rule. I'll just go ahead and use the quotient rule here. So bottom times the derivative at the top. Well, the good thing here is that the derivative at the top is 0. Okay, so we'll have 0 minus top times the derivative of the bottom. And what's the derivative of the bottom? Okay, so we'll have 1 times the derivative of the bottom, and that one uses the product rule. So first times the derivative of the second, we have 2x times 1 over x. Well, let's fix that there. 2x because of the power rule, and then 2x log x times the derivative of log x, which is 1 over x, then plus second times the derivative of the first. Well, the derivative of x is just 1, So I just have log of x squared. Okay, let's go ahead and fix that. Log of x squared. And it's all over the bottom squared. So we'll have x squared times log of x to the fourth power. Okay, the square of a square is a fourth power. All right. Now, again, the denominator is always positive because it's a square. Okay. And so now we just have to check if the numerator is negative. Okay. So we check. Okay, if we clean this up here on top, we'll have to check here that we have negative 2x log x times 1 over x. Well, x times 1 over x is just 1. So I have negative 2 log x minus the square of log x. We have to check if this thing is indeed negative. Okay, where is this negative? Okay, now I can actually go ahead and divide through by the common factor of minus 1. If I do that here, remember, dividing by a negative reverses the sign of the inequality. So we need to check to see if this thing is positive, okay? Now, you can factor this, okay? Take out a common factor of log x. You can factor this as log of x times 2 plus the log of x. And again, we just do the same thing as before. Check, find the zeros, see where this is positive, okay? So we're going to go ahead and build a little sign chart here. Now, think about it. Log x is positive, okay? Let's see here. So log x is positive when x is greater than 1, okay? Log of 1 is 0, and then for any x bigger than 1, okay, we have that the log of x is positive. So we have 1 there. So I know that that's plus, okay? But what about the other factor here? Okay, we have 2 plus log x is greater than 0, which we can write as log x is greater than negative 2. That means that x has to be greater than e to the minus 2, which is a small number, relatively small, okay? But notice here that our sum is actually starting at 2, so we only care about any x's that are bigger than 2. Okay, so here our capital N is 2. We want x to be greater than or equal to 2. And in fact, we actually get that here. Okay, so we only care about this part here. So indeed, f is decreasing on this interval because the derivative is negative here, okay? Remember, we kind of did a roundabout argument here, okay? Let me go ahead and write this back in. We wanted this thing here, wanted to ensure that this thing was negative, okay? It was enough to check that the thing in the brackets, in the square brackets, was positive, because then positive times a negative is a negative, okay? So now we're going to go ahead and do the integral itself. Okay, so we're going to go ahead and look here. The integral from 2 to infinity of 1 over x times the square of log x dx. Again, this is another u substitution. I'll go ahead and explicitly write it here. U equals log x. Instead that du is 1 over x dx. Okay, and when we make the variable changes here, okay, now the integral goes from log 2 to infinity, because log of a big number is a big number. Okay, and then we have, well, okay, u is equal to log x, so we have 1 over u squared dx over x. Okay, it's just du, so we have du over u squared. That's just power rule stuff, okay? Do the usual thing that you do for improper integrals. Okay, the antiderivative of 1 over u squared is minus 1 over u. Okay, we go ahead and evaluate this between t and log 2. So we have the limit as t approaches infinity of minus 1 over t, and then minus minus, which is plus 1 over log 2. Now, as t gets large, 1 over t gets small, and so that's going to vanish in limit. And so our number here is 1 over log 2, and that's a number. So this improper integral converges, so we now say that the sum converges by the integral test. And we're done. So that's a lot, right? We have to find a function, check to see if it's decreasing, okay? Eventually decreasing, do an improper integral, and then see if that corresponding interval converges or not, okay? So the pro tip here is the integral test should be a last resort if none of the tests that we'll be learning soon will end up working for you, or you can't easily spot it. But you can only use this whenever you have a sequence of positive terms, okay? And they're decreasing. Now, of course, you can use this to go ahead and verify the p-test for yourself, okay? That's kind of the proof there, all right? But you see how involved the integral test can get, right? So if it looks like you can actually integrate your thing pretty easily, you may have a hunch that you can use the integral test. But most of the time, it requires a lot more work than it is useful for. But that's all that we got here. That's the integral test right there. Just connecting it back to some actual calculus that we've seen, including that first derivative test, okay? So please go back and review that if you need to. All right. And we're going to be learning some more techniques as we move on through the chapter. I'll see you in the next one.